Hi, everyone. Can you all see the whiteboard?
Yeah.
Okay, good. What answers did you get for the first one? Okay, good. One is correct. Nidhi, do you want to explain?
It's Neil.
Neil, yeah, go ahead.
So basically so first it says two integers have a sum of 26. And then after that, two more integers added to the first two. I said that the first two integers were x and y. And so x plus y equals 26. After that, it says two more integers were added to the first two integers, and the sum was 41. So I did x plus y plus a plus b equals 41.
Mhm.
And then after that, it said finally that when two more integers were added to the sum of the previous four integers, the sum is 57. So I did x plus y plus a plus b plus c plus d.
Okay, good.
So first I split the numbers into like x, y, a, b, and c, d. So I know that x plus y equals 26. So I did that as first. And then after that I did a plus b, and then I subtracted 41 from 26 to get how much the a plus b would be. And it would be a plus b equals 15.
Mhm.
And then after that, I subtracted 57 from 41, and I got 18. So I got C plus D equals 18.
Is it 18 or something else? Close. What should C plus D be?
16.
16, sorry.
Yeah, 16.
So after that, I use after that it says what is the minimum number of odd integers among the 6 integers. And so I know that odd plus odd equals even, even plus even equals even, and odd plus even equals odd.
Mhm.
So 26 is an and it says what is the minimum number of odd integer, which means the least number. So it says x plus y equals 26. So that could be, so that's 26 is an even number. So we could either do odd plus odd or even plus even, but since it says minimum, we should do even plus even because that will make it like, because we need the least number of odd. And so that's the same thing for the last one, C plus D equals 16. Because those that is also an odd, that is also an even number. So we're left with the middle one, which is an odd number. And so if we go, so it says odd plus even is equal to odd. So we know that there should be at least one odd number in that equation. So that's why the answer is 1.
Good. Yep, that's exactly right. So I think the key thing here is, so even if you don't assign variables to each of them, you know that the first two add up to 26. The first four add up to 41. So the two new ones that were added add up to 15. And then now when you add the All 6 of them, you have 57. So the last two add up to 57 minus 41, or 16. So you know 2 integers add up to 26. 2 integers add up to 15. 2 integers add up to 16. So if you want the minimum number of odd integers, ideally we want to make them all even, right? So if I have two numbers that sum to 26, they can both be even. So that's not a problem. If I have two numbers that add up to 16, they can also both be even. So I don't need an odd number there. But when I have two numbers that add up to an odd number, if you think about how can I get an odd number as the sum, one has to be odd and the other has to be even. So in this 15, one of these has to be odd. So the minimum number of odd integers of these 6 would be 1. Now, what if we ask the other question of what is the maximum number of odd numbers among the 6 integers? What would that be?
The answer would be 5.
Good. Why?
Because it could odd plus odd is also even. So, and when the first and last numbers were even, those two could be odd numbers. And then for the middle equation, since that could be odd plus even, that'll be 1 odd. That'll be 1 odd. And when you add 2 plus 2 plus 1, you'll get 5.
Good. Yep, that's correct. So I could have in this 26, both could be odd. When 16, you have two numbers that sum to, you could have, imagine 9 and 7, two odd numbers sum to an even number. So these 4 would all be odd. And again, for the 15, one has to be odd, one has to be even. So one more odd number here. So the maximum would be 5 odd numbers. The minimum would be 1. Good. Any questions on this? Okay, let's move to the second one. Okay. Any answers for this question? Okay, I don't see any answers for this one. Let's start thinking about, let's put in the number 1, n equals 1 here. At least one person in the room, so 1 doesn't actually make sense here. Let's put 2. At least 2 people in this room have birthdays falling in the same month. Is this statement true or false? Do we think this is true or false? So I have 52 people in the room. Is it possible that no 2 people have birthdays following in the same month?
Could you repeat your question?
Sure. So let's pick the number 2 here, right? Where we're asking here, what is the largest value of n such that the statement is true? Let's just say, let's pick the value of n being 2, and let's see, is this statement going to be true or false? So if I pick n as 2, the question is this true? At least 2 people in the room have birthdays following in the same month. And I know there's 52 people in the room. Do you think this should be true or false?
True.
Why?
Well, it could be well, but I think it would be true.
Yeah, that's
Well,
the best.
Yes, because I mean, even if we did one person in like 1 month and then one person in another month, you would have to put all the other 50 people in 10 months. So there would obviously be some overlap.
Good, exactly. So let's look at it this way. I'm making these boxes for each month. Okay, I won't make one for each one, but let's just assume that there's 12 of these. So one is for January, one is for February, and so on. Okay, so I put the first one. So let's say I could kind of put people into buckets for which month they were born. So let's label some of these. Okay, so let's just say we had everything up to December here. So let's say the first person I put in the first month, January. Now the second person, if I put them in January again, then there will be two people in the room having the same month birthday, right? So I want to put it in February to kind of spread them out as much as possible, right? Then I would put the next one in March, the next one in April, and so on. And I have to do this one by one unless I want to have two people in the same month, right? So I can do this up to 12 people, right? Until I have one in each of them. What happens to the 13th person?
He goes back in one of the months.
Good. So the moment I have the 13th person, what must be true?
At least 2 people in this room have birthdays falling in the same month.
Good, exactly. Now, what about this statement? Let's make n equals 3. At least 3 people in this room have birthdays falling in the same month. Sanvi, you're close, but let's see.
Okay, yes, that would be true because then again, you could go another round.
Yep.
The 2 equals 33.
So if there were how many people in the room, would this statement not be true? Or not necessarily be true?
5.
Yeah, so if I have 5 people, yes, doesn't need to be, okay, the final answer is 5, yes, that's correct. But so let's go back to this. At least 3 people in the room have birthdays falling in the same month. If I had, I'm saying now we have 52 people in the room, but if I had fewer people in the room, when could this not be true? Or in other words, what is the minimum number of people I need to have for this statement to be true?
At least 36 people.
It seems like it, but let's think about it. So the first time I put 12 people, right? One in each of the months, right? What happened when I said I'm going to add 13th person?
You put him back in one of the months.
And then what became true?
Then at least 2 people in this room have birthdays falling in the same month.
Good. So I had 12 people there. When I added the 13th person, one of them had to be in the same month as one of the existing people, right? So 2 people had to have birthdays in the same month. Now, if I'm saying 3 people have birthdays in the same month, let's try to use the same logic there.
You would need 25 people.
Good. So I had 2 people in every month. So I could put 24 people and only have 2 people born in each month, right? Okay, sorry, I didn't write in all the other months, but each of them have 2. So there's 24 people. Now this statement is not true, right? At least 3 people in the room have birthdays falling in the same month. In the worst case, I only now have 2 people in each month and 24 people. But when I add this 25th person, right, they have to go into one of these months. And there have to then be 3 people in the same month. Okay, so now why is the answer 5 for this question?
It's because so there are well, you would do 12 times 4 is 48 people, and so that means that there's 4 people in every room. But in order for it to be, but because there's those extra 4 more people, that means that there would be 5 people at least 5 people in a room. So that's why it would be 5.
Good, exactly. So basically, if you think about it, if I wanted to spread them out as much as possible, right? I first put one of them in each month, 12 people, then another 12, another 12, another 12. So when I have 48 people, kind of the most spread out configuration I can have is 4 people for each month, right? Now, when I add the 49th person, one of them has to be in a group that has at least 5. So there must be 5 people in the same month. And this is true at 49 people. So we just happen to have 52 people. And this might be true of actually more. It could potentially be true for more than 1 month. But there must be at least 1 month where there's at least 5 people that share the same birthday. So this idea makes sense.
Yes.
Okay. So this idea is actually something called the pigeonhole principle. It's quite well known and used in a lot of pretty complex mathematical arguments, but the idea is pretty simple. And this is essentially the idea that you're seeing here. And it's basically, you can imagine, I think the context of the original theorem is something with pigeons and holes. So you can imagine each of these months are holes, and you're putting pigeons in these holes. And once you have 1 pigeon in each hole, when you add the next one, at least one of the holes has to have 2 pigeons. That's the essential idea, which is the same argument here. If once I have 12 people, one of them was born in each month. When I add the 13th person, at least 2 of them have to have been born in the same month. Now, this is true even if initially they weren't all distributed as 1 in each month, then there were already 2 in 1 month, right? So kind of there's no way to distribute 13 kind of pigeons in 12 holes without having 2 in 1 hole. Intuitively, the idea is pretty simple, right? If I have some number of holes and more than that number of items, there has to be 2 items in one hole, right? And similarly, you can extend this further, right? If I have 2x items and only x holes, then there has to be 2 in each at like kind of if they're distributed. But if there's 2n plus 1 items and only n holes, then there must be one of them that has 3 items. So that's essentially the same idea here. There's actually another variant or similar question that might say something like, you have a sock drawer with red, green, yellow, and blue pairs of socks. So one of each of these pairs, so there's a total of 8 socks in their drawer. What is the minimum number of socks you can pick to guarantee you have a pair? What would this be?
Eight?
So the total has 8 socks, right? So the drawer has 8 socks in total. If I pick 8 socks in total, I of course will definitely have a pair, right? But what is the smallest number I can pick to guarantee I have a pair?
5?
Good. Why 5?
Because if you pick if in the probability you pick 4 socks of each different color, the last sock will have to be one of the 4 colors, and
Good.
you already have the other one, so it'll be
Exactly. So how does this relate to this pigeonhole principle?
it's kind of like the 2-for-1 thing, because you like you pick you don't need as many picks as you have socks.
Yep, that's correct. So imagine you can name these buckets instead of January, February, March for the months. You now have 1 for red, 1 for green, 1 for yellow, and 1 for blue, right? When you pick a sock, it has to go into one of the 4 kind of groups, right? So if I pick 5 socks, one of these must have 2 socks in it, right? There's no way that I can have all of each sock has to go into one of the 4 groups. And when I pick 4 of them, there could be 1 in each. But when I pick the 5th one, there has to be 2 in one of them. So that would give me a pair. So it's the same idea. This is actually another common problem that's actually based on the pigeonhole principle. But essentially the idea when you're asked like, when each of the items have to be in one group and what is the minimum number you need for something to be true, oftentimes this is the idea to use. Does this make sense? Okay, let's go on to the last one. Okay, 1/3 is correct. Nidhi or Neil, can you explain?
Yeah, so I basically, so because it says Alice randomly selects one ball from her bag and puts it into Bob's bag. So since they have 5, as stated earlier in the question, blue, green, orange, red, and violet, now it's basically saying Bob has 6 marbles and 2 of one color. And I took that color as blue. So 2 blues, a green, an orange, red, violet, and so that's 6 marbles in total. And then what is the probability after this process that the contents of the 2 bags are the same? Basically, one of those blues has to return. So I just said 2/6 is equal to 1/3.
Good, yep, that's correct. So the key idea here is essentially it doesn't matter the first step, right? First, Alice randomly selects one ball from her bag and puts it in Bob's bag. So whichever color she picks and moves to Bob's bag, Bob now has 2 of that one color and 1 of the remaining ones, right? So he now has a total of 6 marbles or 6 balls instead of 5 with 2 of the same color. So essentially now the thing that needs to happen to go back to the original is that one of those 2 needs to go back to the original one, right? So when Bob randomly picks, he's now randomly picking from 6 balls rather than 5. And if he picks 2 of them, whichever are the 2 that are repeated, and puts it back in the first one, there's a 2/6. So there's 6 balls in Bob's bag after the move. 2 are the same color. So if either of those 2 are picked, it'll go back to the same configuration as the initial with the same colors in Alice's bag and Bob's bag. Does this make sense?
Yes.
Good. Any questions? Okay, that's it for today's class then. We'll see you all next week.
Thank you.
Thank you.
Thank you.
Thank you.